Okay, so the next presentation is by Marc Artola from Imperial College London, and he will be talking about nonlinear control of very flexible aeroelastic systems.
Yeah, thanks, Andy, for the introduction. Good morning, everyone. So I will start with a brief outline to the structure of my presentation. I will start with a brief introductory section where I will state the motivation of our research and the status of it. I will follow also with a more theoretical section where I will describe the methods that we use and how we apply them to a numerical example. And finally, with some concluding section. So, start with the motivation. So as most of you might be aware, the latest general trend in aircraft design is to opt for more slender wings and also to use composite or lightweight materials. That has an immediate consequence, which is that the flexibility of these structures increases. And for that becomes essential to use geometrically nonlinear models to capture those effects arising from large deflections and rotations. And there is also the need to use fast or real-time control to be applied to these structures. So for that, we rely on low-order nonlinear structural models, which we will couple with reduced-order models of linear aerodynamics. And for the control and estimation purposes, we will use model predictive control, which we will couple as well with moving horizon estimator. So this is just a brief recap of what I presented back in the last ConFlex meeting in Bilbao. There I showed how we developed our structural model and how we constructed our optimal control solver, which we then used to underpin this model predictive control to solve mainly structural problems. So the main developments from then is that we've developed our aerodynamic model. We have implemented moving horizon estimator. We have done some research as well on how to include Kelvin void damping within the intrinsic beam formulation, and also how to address multi-body dynamics within this same framework. So for the rest of the presentation, I will focus on showing you the main results, the latest results in the control and estimation of aeroelastic systems. So let's get started with a bit of theory. So for the structure, we use the intrinsic nonlinear beam equations. The first equation is the equation of momentum balance. Second equation is the compatibility equation. So why is it called intrinsic? Because it's based on velocities and strains as our main variables. So x1 would be the vector of linear and angular velocities. x2 would be the vector of sectional forces and moments, which if we multiply by this C, the compliance matrix, we get the strains. I also forgot to mention this M matrix is the inertia or mass matrix. So as Charlotte mentioned yesterday, by using this set of variables, we can express the dynamics, the nonlinear dynamics of these kind of beams by using first order, both time and space derivatives, and also with nonlinear quadratic terms, which gather effects such as gyroscopic effects or other geometrically nonlinear effects. Just to mention that standard linear formulations are included in this more general nonlinear framework, which would be simply obtained by crossing out the nonlinear terms and setting the certain stiffness parameters to infinity if we want to get either an Euler-Bernoulli or a Timoshenko beam. So for the aerodynamics, we rely on potential flow theory, which has the assumptions of inviscid flow and also incompressible flow. And in this scenario, the Navier-Stokes equations reduce to solving this linear Laplace equation, which looks very innocent. It's a linear PDE, but we have to satisfy also this set of constraints, which is the non-penetration constraint of the velocity at the solid walls, And also, we have to match the far field velocity at infinity. So as I said, this is a linear differential equation. We can make use of the superposition principle. And for this general case where we have a lifting surface, which we can see here, and also the wake it generates, we can just construct a general solution by using this superposition principle, where we distribute singular solutions along the surface of the lifting body, but also along the wake of the that it generates. And we also have to add up the potential of the far flow, or like the background flow. So as I said, this might look an innocent set of equations. However, by this non-penetration condition, nonlinearity is introduced to the system, since this allows for arbitrary kinematics. So if we have structures which deform, this set of conditions vary with time, and that complicates things. And also, well, just to mention that for a 3D case where we can have a wing like this, a general solution would be obtained by spreading or by distributing a continuous two-dimensional vortex sheet, both along the main wing and also along the wake. This has been so far the set of PDEs which describe our system. So now we turn to finite dimensional modeling to obtain a model which will be amenable to control. So for the structure, we use what we call this model-based finite dimensional system. It consists of computing the linear normal modes of the structure, this phi1, phi2, which are the eigenfunctions of the linearized intrinsic equations around the origin. We assume that we can build approximate solutions in a separation of variables fashion, where we take each mode, we multiply it by a temporal coefficient, and we substitute these expansions into the original PDEs, where we perform a Galerkin projection, and we obtain this set of nonlinear ODEs in terms of these temporal coefficients. We notice that this is still nonlinear, so we are able to retain the nonlinearities, and essentially that allows us to capture those nonlinear effects I was speaking about before. So for the aerodynamics, we make use of the unsteady vortex lattice method, which basically consists on discretizing the continuous vortex sheet that I mentioned before into a discrete vortex lattice. I also said that this is nonlinear in nature, because the non-penetration boundary condition has to be satisfied for arbitrary kinematics, but we can linearize the system about an arbitrary reference. However, the resulting system sizes are very large, so we have to turn to reduced order techniques, and we will use this set of structural modes as projection matrices to apply then these reduced order modeling techniques. And the resulting aeroelastic system is obtained. Some more details about how this implemented can be found in our last year paper of SciTech. And finally, just to briefly mention which are the estimation and control strategies that we use. We use a moving horizon estimator and model predictive control for the control bit. Both are similar in the sense that they can account explicitly for nonlinear dynamics. They provide estimation and control by repeatedly solving these open loop optimal control problems, which are subject to several constraints. And we use multiple shooting, sequential quadratic programming to solve them. The main differences is that for the MHE, the optimization is performed over past time horizons, and the decision variables are the disturbances to the system and the current state of the system. And the cost function which we try to minimize has this shape, which essentially penalizes the difference between the measured outputs that we get from the real system to the output that we get from the internal system that the MHE uses. The MPC counterpart, well, the optimization is done over a future time horizon, while the decision variables is the control input, the control load. And the cost function is mainly a penalization from a reference state that we want to achieve. So this is, well, we move to the numerical example section. For that, we will apply this methodology to the PASI wing, which is a very flexible clamped wing bench test, which has been constructed at Technion University, which has these geometrical characteristics. So it has a span a bit more of a half a meter and a chord of 0.1 meter. And we first do a gas load alleviation problem. Here you can see the 3D view of the wing, the side and front view of the wing together with the aileron input. Here we see the wings, the vertical coordinates of the wingtip as a function of time together with the control input, which is the aileron deflection. So for this case, we use a model constructed with 9 structural modes, and well, this is the sampling time that we use. But essentially, the most important things that I want to outline is that the moving horizon estimator measures the linear velocity at 4 different sections, stages of the wing, and the MPC penalizes mostly the velocity and the forces and the stresses, the forces and moments of states from this trimmed condition before the gas hits the wing. And in this case, we apply a severe constraint on the control input just because we want to test that the controller is able to handle these large deformations that we have been observing. So then we also set up a flutter suppression test problem. So this wing offers us is a very rich case regarding these flutter suppression problems. So what you see here is a flutter plot where we plot the eigenvalues of the linearized system around the non-linear equilibrium points for varying incoming flow velocities. So we see that as we start to increase velocity, the wing remains stable. However, for a range of velocities, which is about 40 to 50 meters per second, one of the eigenvalues crosses the border, goes to the right half plane of the complex plane, and the system becomes unstable. But if we increase a bit the velocity again, the system is stable until a further increase in velocity where the system becomes unstable again. So there's a region of velocities after 50 meters per second where the system is stable. So this graph can also be interpreted as a stability analysis instead of versus velocity versus deformation. So we see, because it's every equilibrium point it's a nonlinear equilibrium point. So as we have more velocity, we have more deformation. So we see that for certain levels of deformation of the wing is stable and there is no flutter. So that we will take that into account to understand how the controller works for some cases. So in this case, if we opt for a sample time which is rather small, we take the MHE using more or less the same parameters. But the MPC, we mostly penalize velocities. We see that the controller opts for this direct actuation, where the flap is deflected in an oscillatory manner to counteract the oscillations provoked by a flutter. And we observe a substantial reduction in these oscillations. However, if we increase the horizon of the model predictive control and we penalize further the velocities at the end of the horizon, we see that the controller opts for this other smoother solution, where what it does is essentially what I was speaking about before with that graph. It brings the main structure to a more deformed state where the where flutter is no longer happening. And this essentially is a nonlinear behavior, which is well captured by the controller. Okay, so time to reach some concluding remarks. So this is the summary of the main achievements of my project. We have been able to come up with this efficient modal-based aeroelastic model, which describes fairly accurately flexible aeroelastic systems, and most importantly, that the state sizes or the system sizes are amenable to control. We have used them to underpin these MPC and MHE frameworks, which leverage the compact and neat structure of the underlying equations, and that has allowed us to explore scenarios where nonlinear control is essential. We are also quite proud about the developments that we've done modeling structural damping within the nonlinear intrinsic formulation, and some ongoing and future work. So we are working now to interconnect this controller framework to SharpEye, which is Imperial's in-house nonlinear aeroelasticity package. So this is the second flutter suppression case that we saw before, just run on this medium to high fidelity software, which it allows us to show these pretty cool or fancy simulations. And then, yeah, the natural next step is to extend these to full aircraft models. I think that will keep us busy for the next months. And also we plan to work in a modal-based parametric model to be applied to multi-body configurations, which we are confident that will allow us to enable fast control of structures like hinged wings, in which we are quite interested. And well, this is finally the list of publications. So 3 accepted conference publications. We have 2 submitted papers into in journals which are under review. One in the IEEE Transactions on Automatic Control, where we describe the main theory behind this model predictive framework, and another one regarding this Kelvin-Voigt damping. And we also have this other journal which we